Okay, so today we're going to discuss examples of when you would use the Wronskian in a practical problem. So let's say you're given a problem, right? And so the model for the position y of a particle on a wave is given by, or could be represented by, the differential equation y equals negative y double prime. So, and then they give you two initial conditions. So at time t equals 0, the position y is 4. And then at time t equals 0, the speed of the particle, the instantaneous speed of the particle is, wait, let me stick some units. So 4 meters, and then the instantaneous speed is 3 meters per second. Okay, so there you have the two initial conditions, and you know you need those two to solve for the C1 and C2 in your particular solution to that problem. Okay, so this problem is asking you to find both the general solution and the particular solution. So again, in order to find the particular solution, you have to solve for C1 and C2 in the general solution given those two initial conditions. Okay, so since we don't really know how to solve y equals negative y double prime yet, the only way we can really get some functions that work within that is to guess. So possible solutions with the guessing method, which is always effective. So by looking at that, you might be able to guess that cosine works. You know, the first derivative of cosine is negative sine, and the derivative of negative sine is negative cosine. So there you get that the second derivative of cosine is equal to the negative of cosine. Okay, so and then another one you might be able to guess is sine. So again, the first derivative of sine is cosine, the derivative of cosine is negative sine, so you get that the second derivative of sine is equal to the negative of the actual function. So here we have our y sub 1 is cosine and our y sub 2 is sine. And so you might be wondering, oh, you know, if we combine those two, can we get a general solution? Could the general solution be of the form C1 cosine theta plus C2 sine theta? And recall that you can only do this when that r of t in the standard form is 0. But if we can rewrite the above differential equation as y double prime plus y equals 0, and so we can see that that constant coefficient, or that constant function that the differential equation equals, is indeed 0, and so you can do this trick with combining different solutions to form another solution. And so how do we check that this is the general solution? Well, you check using the Wronskian. So the Wronskian is the determinant of that linear system of equations, and you know that if the determinant is never equal to 0, then you know that you can always invert that matrix, and if you can invert that matrix, then you can solve for that C1 and C2 within the general solution. So let's take a quick refresher as to what the Wronskian is. Like I said before, it is the determinant, but that determinant of the matrix would be y1, y2, y1 prime, y2 prime, and so the first item would be cosine theta, as that is y1, then sine theta, as that is y2, then y1 prime would be negative sine theta, as that is cosine prime, and then the derivative of sine theta, which is cosine theta, as the bottom right entry. And so we have to prove that the determinant of that matrix never equals 0. And again, if it never equals 0, then it's invertible. And if it's invertible, then you can solve for C1 and C2. And so in this case, the theta is equal to the initial time. And I'm just writing theta because it's convenient and a habit to write theta after trig functions. So, but when you take the determinant of the Wronskian, you're not just proving it for one initial condition. So you're not just proving it for the initial conditions that they give you within the problem in the beginning. Those are used to solve for the particular C1 and C2. You want to prove that the Wronskian holds for every single possible initial condition. Because if it does, then you know that that general solution works for every single possible initial condition. And if it does, then that's what truly defines a general solution. So again, it's for any initial time and not just the ones that are up there. So here, like, you might be tempted to say, oh, let me just put in the initial time, which was 0, and then the constant coefficients, and then what those initial conditions were equal to, which was 4 and 3. And you might say, oh, you know, that's my system of linear equations, and I'm trying to solve for that. But no, that's not what you do, because you have to prove it for every single initial condition and not just the one specified. Alright, so since you know what not to do, let's see what you do. Okay, so you're trying to prove that this thing, let me do this in red. Okay, so you're trying to prove that this entire thing, this entire thing is never equal to 0. Never equals 0. Alright, not just that it doesn't equal 0 for the specific initial condition given by the problem over here, it's just that it never equals 0 for any initial condition. And so if you prove that it never equals 0 for any initial condition, then you know that the general solution, where is that? Then you know that this thing right here, then you know that this thing is a general solution for the differential equation here. Okay, so let's start by trying to take the determinant of this. Okay, so the determinant would be cosine theta. Again, theta is equal to t initial, and I'm just writing theta because that's a habit of mine. So cosine theta minus negative sine theta sine theta. Okay, so that simplifies. Cosine squared theta plus sine squared theta. Okay, so what do we know about cosine squared theta plus sine squared theta? This equals 1. 1 is never equal to 0. Therefore, since 1 is never equal to 0, C1 and C2 can always be solved for with any initial condition with the general, provided that the general solution is of the form of here. And so because C1 and C2 can be solved for any initial condition, then this is indeed a general solution. So, gen solution C1 cosine theta plus C2 sine theta. Okay? And the question asks, I believe, for a particular solution as well to those initial conditions, but that requires a lot of algebra, and I'm sure you guys all know how to do algebra, so we're just going to stop here.